Okay, welcome to the visit training session entitled Use of VIIRS Imagery for Tropical Cyclone Forecasting. My name's John Naff. This is a presentation prepared by myself and Galina Cherakova. Okay, the first thing we'd like to do is define VIIRS. VIIRS is the infrared imaging radiometer suite. It will be flown on the next generation of polar satellites for the United States. These include the SUMI National Polar Orbiting Partnership, or SUMI MPP satellite, which is currently in orbit, as well as the Joint Polar Satellite System satellite version 1 and 2, JPSS. JPSS-1 will be launched later this year. VIIRS is a global visible and infrared instrument. It covers the Earth twice a day and has 22 channels with a 750 millimeter resolution. One of the big upgrades with the VIIRS and infrared imagery on this instrument is that the width of the swath is 3,040 kilometers. This provides no gaps, particularly in the tropics, and complete coverage. One of the unique channels on the VIIRS suite of instruments is the day-night band. It has a really large sensitivity ranging from full sunlight reflection to faint air glows. The image quality is variable depending upon the amount of coverage and the lighting in the scene. The VIIRS day-night band provides two primary functions for tropical cyclone forecasting. It's an aid for center fixing and an aid for eye detection. The day-night band also detects instantaneous lightning and night glow. Both of those topics will be covered later in this presentation. Center fixing is the starting point for most of the tropical cyclone and warning process. It's also the starting point for intensity and motion estimates when you're using satellites. Weaker systems can be difficult to center fix because of their large asymmetries and occasional multiple centers. Sheared systems can also have the same difficulty making the center fix, as the low-level center is sometimes detached from the deep clouds. This is a case when VIIRS imagery and day-night band in particular made a difference in an operational decision. In this case, this was Tropical Cyclone Flossie as it approached the big island of Hawaii. At this time, the deep convection in the infrared image here on the left is located in this region. The day-night band, which is shown here on the right, you can clearly see that the image indicates that the low-level center is located up in this region here, whereas the deep convection is down in here. And so from this imagery alone, the operational decision was, and conclusion was, is that the low-level center was north of Hawaii and is displaced from the convection. This results in two operational decisions. One is the southern island is probably not going to be affected by this tropical cyclone, and two, the cyclone might be quite a bit weaker than anticipated if the center was under the deep convection. In this case, we're looking at a weak tropical cyclone that has not been classified as a depression or named as a tropical storm. In this case, the day-night band shown on the left clearly shows that the low-level center in here is well displaced from the deep convection that shows up in the IR image to the right over here. In this case, the operational decision might be to drop this invest and not anticipate further intensification of this system. In this case, we have a tropical storm strength system that in the day-night band, the low-level center has been shown to be well detached from the deep convection. So the important decision here might be to anticipate this storm has now begun a period of rapid weakening. You may also want to relocate the center based on this image, and this should affect operations going forward. This is yet another case of a displaced low-level center. In this case, we have a tropical depression, which is strongly sheared from the east. We also have indication of overshooting tops here and over here in the visible, as well as a cold overshoot in the infrared here and a warm overshoot in this region here. If you were to locate the center based on the infrared in this region here, you may have an intensity that is closer to 50 knots, whereas if you properly locate the center on the edge of the deep convection in this region right in here, this storm would likely not be classified as a tropical storm or borderline tropical storm at the strongest. So this would affect, and in fact in this case this storm was never classified as a tropical storm but remained a depression its entire lifetime. In this slide we shift focus to eye detection. In the visible or day-night band, you can see that we have a cleared out eye feature. However, in the deep convective signature shown in the infrared, we would put the center in this region here, but based on the day-night band, we might want to move the center closer or a little bit further to the left or west. This would also affect future intensity estimates, as the center will be now in a different location. In this case, we have a banded eye situation. The banding eye can be clearly seen in the day-night band. In this case, there is no banding evident in the infrared image. It's very difficult to determine the structure of the system at this time at night, based solely on the infrared. Banding eye, however, in this case may allow the analyst to upgrade this system to a hurricane strength system rather than a tropical storm strength system. So this is, in addition, this signature is often seen with storms that are rapidly intensifying. So if you had animated infrared images and you saw that these individual cells were also rapidly moving around the cyclone, it might also provide you a little bit more evidence that you have a rapid intensification, or at least more rapid than climatological intensification for this system, and might be willing to change your forecasts. In this case, again of Ramasoon, there's evidence in the day-night band of concentric eyes. It's very difficult to discern in the infrared imagery on this side. You can clearly see both the relict eye and the mote in the day-night band. So how this might change your operational decision is that in this case you might, in the short term, maybe 12 or 24 hours, may forecast weakening or steady intensities, followed by a period of more rapid intensification thereafter if the environment remains favorable for intensification. In this case, it's important to understand that the sensitivity of the day-night band allows for the instantaneous detection of lightning. So this image shows lightning in the eye wall and out in some of the surrounding rain bands. In most cases, this will be a distraction from your analysis of the cloud tops in the day-night band. But there is some evidence that lightning in the eye wall is often associated with near peak intensity. In fact, in this case of Hurricane Amanda from 2014, this image was within 12 hours of this storm peaking in intensity, according to the Dvorak estimates from TAFB. This slide shows another potential distraction from normal imagery or tropical cyclone imagery analysis. In this case, the night glow is showing gravity waves that appear to be emanating off of the islands north of the tropical cyclone center. These do not show up in the infrared imagery and do not affect anything in their analysis. However, someone using the day-night band should be aware that these gravity waves will sometimes show up in the night glow. In this case, the day-night band on the left shows evidence of both gravity waves in the night glow and lightning activity in the eye wall. Forecasters should be aware that day-night band imagery is available over tropical cyclones from CIRA. Imagery is shown in near real-time and archived for case studies and best track activities. The day-night band has about a 2-hour latency and will be available or will be most available to operations and should be available during the hurricane season. Work continues to improve all aspects of this imagery. Participants should be also aware that COMET has more information about VIIRS and its uses at these websites. Even more information about the VIIRS, both in training sessions and individual tropical cyclone cases, can be found at Visit and at CIRA at these websites. Here I present the references that were used in this presentation, and here I would like to acknowledge that this work was supported by the JPSS Risk Reduction Proving Ground Program, the Sandy Supplemental Funding Program, and VISIT here at Colorado State University. Thank you for your time.